Hello everyone, in this video we are going to take a look at electrical transmission lines, which are essentially a pair of conductors designed to take an electrical signal from one place to another. And it could be a pair of parallel wires, as I've sort of drawn in my diagram at the top left of the screen. It could be something else like a coaxial cable, but that's a little bit harder to draw. So we can visualize it as a pair of parallel wires. And the question we're going to address in this video is how do the current and voltage behave on a transmission line? In other words, how do they vary along the transmission line and how do they change with time? Now, just to set up the basic parameters of the problem, I've defined the current coming into the top wire as I, and by conservation of charge, the same current should be leaving the bottom wire. We've defined the potential difference of voltage between the wires as this V. And I've also defined an x-axis to sort of tell us how far along the transmission line we are. And so the I and the V can be functions of both position x and time t. So we want to find the x and t dependence of those quantities. Now, as with many things in physics, the voltage and current are going to be governed by differential equations. And to see why differential equations are relevant here, we're going to zoom in and sort of imagine that we're looking at an infinitesimally small part of the transmission line. And we are going to say that it has a length of dx, a small interval of x along our x-axis. And we can define some other infinitesimal quantities. We can say that because the current is varying along the length of the transmission line, the current going out of this wire at the top is not necessarily the same as I. We're going to call it I plus di, so I plus some small change. And similarly, that same current, I plus di, is going to be going in to the wire at the bottom. And then predictably, I am going to define a voltage at the far end of the transmission line. It's not necessarily the same as V. We're going to call it V plus dV. So it's changed a little bit compared with the voltage over at the left. Now, why are the voltage and current actually varying in the first place? Well, it's because the wires are interacting with each other. They're going to be interacting in a couple of ways. Firstly, there is going to be an inductance between the wires because each wire is producing its own magnetic field, and some of the flux due to that field is sort of threading through the area, the region between the wires. So there's going to be some inductance for that reason. There's also going to be some capacitance between the wires. In other words, sort of there'll be an effect on the voltage between the wires due to the buildup of charge at various different points on the wires. Whenever you put two conductors next to each other, there'll always be some capacitance between them. And there's also going to be a resistance, right? Like in reality, unless we're talking about superconducting wires, then there is going to be some resistance to take account of. So we can actually represent the inductance, capacitance, and resistance on our little diagram as if they were separate elements of the circuit. So let's do that. Let's add some of those on. I'm going to start by drawing my capacitor. Now the capacitance is between the wires, so we're going to draw that, well, between the wires, connecting them up like that. And the inductance and the resistance, we can put those in either branch, but let's just put them both on the top branch. Let's draw an inductor there, and let's draw a resistor there. You might be used to depending on where you're from, you might be used to seeing resistors drawn as zigzags instead, but I'm used to drawing them as little rectangles like this. So we have a capacitor, inductor, and a resistor. Now, the most sensible way to define the capacitance, inductance, and resistance is per unit length, because we're considering a certain length dx of our transmission line. So we're going to say that the capacitance per unit length is C, therefore the capacitance of this capacitor for this little element is C dx. Similarly, the inductance per unit length is going to be L, so the inductance is L dx, and same for the resistance, we're going to call it R dx rather than just R. So now, armed with this diagram and the parameters R, L, and C, we can start to construct our differential equations. So first, let's consider the small increment in voltage dV. Right? Remember, the voltage goes from V to V plus dV as we go from one end to the other of this little infinitesimal bit of the transmission line. Now, from the diagram, V is just the voltage across the capacitor, whereas V plus dV is the voltage across the capacitor, inductor, and resistor, right? It's the voltage basically from that point to that point. And so the extra voltage, dV, is basically the voltage across the inductor, VL, plus the voltage across the resistor, VR. And we have standard expressions that we can use for voltages across inductors and resistors. For an inductor, it's minus L di by dt, but here it's really L dx di by dt, because the inductance is L dx, right? Di by dt, whereas that's the time rate of change of the current. This is basically saying that inductors resist changes in current, right? It's you've got this minus sign here because when the current tries to increase, the inductor produces an EMF that tries to prevent that increase, and vice versa. When the current tries to decrease, di by dt is negative, then the inductor produces a positive voltage. So that's why that minus sign is there. What about the voltage across the resistor? Well, we can just use Ohm's law, V equals IR. So we're going to have a minus I R dx. Remember, the resistance was really R dx. And it's negative because it's a voltage drop, right? Some energy is lost as the current flows through the resistor. So can we do something similar for the little current increment di? Let's see, di. Well, notice that from the diagram, we have current I coming in on the left, current I plus di going out on the right. So that means the current, the extra di current must have come from this branch where the capacitor is, right? There must be a current of di flowing through our little imaginary infinitesimal capacitor. Now, current is the rate of change of charge over time, and we know how to calculate the amount of charge on a capacitor from the capacitance, right? The charge stored on a capacitor is the capacitance times the voltage, and so the current di through the capacitor is the time rate of change, d by dt, of the capacitance, which is C dx, times the voltage across the capacitor, which is just V. And the only thing here that depends on time is the voltage, and so that's really C dx times the derivative of V with respect to time. But we've got to think carefully about whether we need a plus or a minus sign here. So the way I think of this is, if di is positive, so suppose that di is positive, from the diagram here, that means that we're building up some positive charge on the bottom plate, right? We're building up positive charge on the lower plate of the capacitor. Therefore, the potential at the lower plate of the capacitor is going up, right? Potential is high when you're close to a positive charge. So if di is positive, we're increasing the potential of the bottom plate, and conversely, we are decreasing the potential of the plate at the top, right? Because if charge is flowing, if di is positive, positive charge is flowing away from the top plate is becoming more negative, and therefore it's getting a lower potential. So if di is positive, the conclusion is we're increasing the potential of the lower plate, but decreasing the potential of the plate at the top. So that's bringing the potentials of the top and bottom plates closer to each other. Therefore, the potential difference across the capacitor is getting smaller. So V is getting smaller. V is decreasing with time. So our conclusion from all of that physical reasoning is that when di is positive, dV by dt should really be negative, and vice versa. So I actually need to put minus signs in front of both of those expressions. There may be other ways to justify that minus sign as well, but personally I always find it much easier to try and justify things like plus and minus signs on physical grounds rather than purely mathematical grounds. So in each of the equations that we formed, the one for dV and the one for di, we have differential quantities on both sides. So we could divide through by dx. We've got dx here, here, and here. Divide through by that, take the limit as it goes to 0, and end up with a partial derivative. If you do that for the voltage equation, you find that dV by dx is going to be minus L di by dt, and then just minus IR. I'm going to label that equation 1. And if we do the same thing for the di equation down there, we find that di by dx is just minus C times dV by dt. Let's call that equation 2. So we have a system of coupled first order partial differential equations. They're coupled because they both involve derivatives of V and I. Now you can actually separate the V and I into separate equations provided you're willing to turn them into second order differential equations. So the way to do that is just differentiate both equations. Let's differentiate the first one with respect to x and see what happens. I'm going to say d by dx of equation 1. Well, the left-hand side is now just the second spatial derivative of the voltage, dTv by dx squared. The right-hand side, you're going to get minus L and then a mixed partial derivative, d2i by dx dt. And then r is a constant, and so we just get minus r di by dx. Now, the most interesting term here is this middle one, this mixed partial derivative, because we can get another expression for that mixed partial derivative of I from equation 2, if you think about it, by taking equation 2 and differentiating it with respect to time, because then you get d2i by dt dx equals minus c, and then just d2v by dt squared. And so we have an expression for d2i by dt by dx, provided that we're willing to accept that second partial, or the partial derivatives commute, and d2i by dx dt is the same as d2i by dt dx. I'm not going to prove that here, but provided we're willing to accept that these two things are the same, you can substitute one in place of the other. So if we go ahead with that substitution, we still have d2v by dx squared on the left. We're going to get minus L times this whole thing that we just derived, which is minus c d2v by dt squared. And then we've got this r minus r di by dx. What are we going to do about the di by dx? Well, equation 2 tells us what di by dx is, right? It's just minus c dv by dt. So we just substitute that in, minus c dv by dt. And the nice thing about this is this equation now purely involves voltage, doesn't involve current. So if we tidy things up a bit, put everything on the same side, I am also going to divide through by LC. We're going to get an LC when we expand those brackets. If I do that, I'm going to get d2v by dt squared because I divided the LC out. I'm going to get plus r over L dv, let me write that more nicely, r over L dv by dt, because you would have had rc and we divided by LC, and the c's cancel. And then I'm going to also move the second spatial derivative on the same side and write it as minus 1 over LC d2v by dx squared. All of that stuff is equal to 0. So we have a second order partial differential equation for the voltage. We can get a very similar one for the current. I won't go to the full details of that because it's very similar to what we've already done. But the basic idea is that you do the, when we did this differentiation in the middle of our working there, we could differentiate equation 2 with respect to x, and then equation 1 with respect to time. So do the derivatives the other way around, and then you could eliminate the voltages and you get a similar equation for current. So I'll leave that as an exercise for any enthusiastic viewers. It works out the same, I have checked, and you get d2i by dx by dt squared plus r over L di by dt minus 1 over LC d2i by dx squared is equal to 0. So I and v actually obey the exact same equation. So now we'll go in to think about what the physical interpretation of this equation is. So let's just focus on the voltage partial differential equation. Remember that the same arguments could apply to the current one because it's the same equation, but let's just deal with the voltage for the time being. So it's conventional to group some of these parameters together and sort of relabel that. I'm going to call r over L gamma. I'm going to call 1 over LC u squared. Now, the reason for this is, well, this equation may or may not look familiar. It's actually the wave equation. It's a damped wave equation. And the u, if you call 1 over LC u squared, then it turns out that u, in other words, the square root of 1 over LC, or 1 over the square root of LC, is the speed of undamped waves propagating along the transmission line. It would be more conventional to call that c or v for wave speed. However, those are both taken by capacitance and voltage, so I'm using u here. Now, if we imagine some typical boundary conditions, right? Let's say, for example, if V of 0 and t, in other words, the voltage at the far left end at the source of the transmission line is some known function. Let's just call it V subscript 0 of t, right? That could be coming from a signal generator. It could be some complicated signal. It could just be like a sinusoidal signal. But the voltage is some specified function when x is 0. Then it is approximately true. I'm going to say V of x and t is roughly equal to e to the minus gamma x over 2u times this v0 function evaluated at t minus x over u. So I am just quoting this. I do have another video. If you're interested, I've got another video deriving this same solution in the context of waves on a string, but it's the same maths. You can do this, for example, using the Fourier transform. That's worth like a whole video on its own. So I'm not going to derive it again. Go have a look at that video if you're interested. I will note this solution applies only when the damping is relatively small. And I'll say a little bit more about that in a moment, like what the damping actually is in this context. But the physical interpretation of this solution is that you have a spatial decay. So your signal decays spatially as you move along the transmission line. And this bit here, this v0 of t minus x over u, it's basically saying take your v0 function and evaluate it this much in the past, like a time x over u in the past, which is consistent with the interpretation of u as being the wave speed. So this solution is basically telling us that the wave that we create at the far left end propagates along the transmission line, but also decays as it does so. So let's briefly consider what happens as we vary R, L, and C, just to get some physical intuition for this. The easiest one to consider is R. So let's say R increases. We increase R. Well, that doesn't affect U, but it does affect gamma. Gamma gets bigger. And if gamma gets bigger, because it's in the exponent, your spatial decay occurs more quickly, right? So if R increases, then you get a sort of quicker spatial decay. Your wave doesn't propagate so far along the transmission line, which makes sense because resistance is basically causing an energy dissipation, right? It's energy loss, and your wave is losing energy as it goes along, and so the signal is going to decay more quickly if there's more resistance. So what about the capacitance? If we increase the capacitance, what's going to happen? Well, the capacitance appears in u squared. U is 1 over root LC. So if we increase the capacitance, the wave speed is inversely proportional to root of c, and so we get a slower wave. So the wave actually propagates more slowly. And as a direct result of that, because you have this u in the denominator of the exponent, simply because the wave is going more slowly, you also get, again, a quicker spatial decay. But the reason is different this time, right? It's not to do with dissipation. It's just because the wave is not going as quickly, so it doesn't get as far before it decays to a certain amount. Now, can we get some intuition as to why high capacitance means a slower wave? Well, the way I would think about it is, remember that, well, think of the equation V is Q over C for a capacitor, right? The voltage due to a capacitor is the charge on the capacitor divided by the capacitance. So if you have a bigger capacitance, then that's like saying the voltage due to the capacitor for a given amount of charge stored is smaller, right? If you increase your capacitance, you get less voltage per unit of charge stored. And so that is going to mean, in the context of this transmission line, that the cables are basically less good at communicating with each other, right? The capacitance between them can soak up bigger differences in charge without creating a very big voltage, and therefore the cables are not communicating information as well if the capacitance is very, very large. And therefore it makes sense that the wave would be going more slowly. Finally, what about the effect of the inductance? If we increase L, similarly to the capacitance, well, U is inversely proportional to root L, so you get a slower wave as well. Something interesting happens with the decay, though, because gamma and U both depend on L, right? So if we have increased L, we have slowed down the wave, but we've also decreased gamma, right? Because gamma is inversely proportional to L. Now, because gamma is inversely proportional to L, but U is only inversely proportional to root L, overall, right, this gamma over U combination actually gets smaller, and therefore we reduce the decay, right? So there's a slower wave, but actually there's less decay. It will propagate further into the transmission line before decaying. So how can we interpret why that is? It basically goes back to what we said near the beginning, where we said inductance provides a resistance to changes in current. Inductance is like inertia for current, right? And so if there's more inertia, it's kind of harder for a wave to propagate, right? But it's also harder for a wave to stop when it's already propagating, right? So it's harder both to start a wave propagating and also for it to come to a stop. And therefore, even though your wave goes slower, it will get further once it's already got going, right? And so we can come up with these nice little physical explanations for what happens when you change all three parameters R, C, and L. Anyway, that's all for this time. Thank you for watching, and I'll see you again soon.